Wim, you want to give me a description of what's going on in this graph? Okay, so this is the temperature of a solution of water and these particular substances. It's not all of these substances together, but it's this, it's this in water and then separately that in water, right? So, okay, what's going on here? What do we have as our axes titles? What's on the bottom axis title? Temperature in degrees Celsius. And what's on the vertical axis title? Solubility measured in what?
Grams per water.
Grams per 100 grams. So we're basically saying this is a percent concentration, right? So we're saying at what? At 0 degrees Celsius, what is sodium chlorate? What's the solubility of sodium chlorate? 80 grams per 100 grams of water. You're basically saying this is like an 80% solution of sodium chlorate. Right, that's basically what we're saying. Not really. Okay, it gets complicated when percents get really large because you have to take into account the mass of the solute as well. But whatever, that's fine. So let's just go through this. Which compound has the highest solubility at 20 degrees Celsius? How would you answer that question? What would you do? Somebody describe for me how to go about answering the question. Aaliyah?
Find 20 degrees Celsius on your x-axis.
Find 20.
And then go up and find where's the highest.
And then find which substance happens to be the highest solubility. So we go up, and I see this thing right here. What substance is that? NaClO3. That's sodium chlorate, right? So we've got sodium chlorate is the compound with the highest solubility at 20 degrees Celsius. Now, what is the approximate solubility of potassium nitrate at 60 degrees Celsius? So somebody tell me how I would go about solving this. Not what the answer is. Kylan, you don't want to tell me how to solve this? Nope. Okay. Anybody else?
You're good.
Wim?
So for like the 60 degree thing on the graph,
Yeah.
Up where one is on
On KNO3, right?
go over and see where it goes on
And then follow it over. And so what is the approximate solubility?
110.
What? You can fit 110 grams of potassium nitrate inside 100 grams of water. Pardon?
So look at the top of the graph.
I know. So would you agree that for a lot of these compounds, they have relatively low solubilities at low temperatures? And would you agree that many of them have very large, high solubilities at higher temperatures? Yeah, hopefully that makes sense. Okay, so we say it's 110 what? 110 what? Grams per 100 grams of water. Loosely speaking, that's like saying your solution is 110% sodium chlorate, which is kind of an impossibility. That's why you have to take into account the mass of both things now. Which substance has the solubility that is least affected by temperature? Would you agree that sodium chloride is a substance that's least affected? Perfect. And then the substance that's most affected by temperature. Yeah, that potassium nitrate. It starts out as the lowest solubility compound, and it ends up as by far, if you kept this going, right, it would end up being by far the highest solubility compound. Yeah, so it's a dark horse, that's right.
Oh, black. Oh.
Black horse, yeah, same thing, right? Okay, does this graph make sense to us? Now, I want you to understand that I'm not necessarily going to give you a graph on the test. I just thought this was a good way of practicing graph reading skills. Would you agree that we haven't seen a ton of graphs this semester in Chem 20?
Yeah, thanks.
Yeah, this is basically the first graph we've seen. So, okay, solubility of gases in water. Which substance has the solubility that's least affected by temperature? It looks like helium, probably because it starts out the lowest as well, and it's only going to get lower as you increase temperature. Which substance has the solubility that's most affected by temperature? Methane, again, that's because it starts out as the highest solubility, so it's most affected. Okay, what can you tell me if I wanted to dissolve the maximum amount of carbon monoxide in water? What would I have to do to that water? Would you want, does carbon monoxide have a higher solubility at hot temperatures or cold temperatures? At cold temperatures, right? And that's exactly what we learned about yesterday when we were learning about factors that affect solubility. Are we okay with that? You can just keep that, you can just tuck it into your notes or whatever, you can recycle it, it's all good. I'm never going to ask you to hand it in. I would keep it if I were you, that's fine.
Do we have a graphical lesson finally?
Nope. Good. Good. Have we seen this before?
Yes.
Have we? Oh, so good. The shake, yeah. Okay, what compound do you want to talk about? Strontium phosphate, silver bromide, we're not going to do thallium sulfide, copper 1 iodide, or mercury 2 bromide. Which one? Hands up for strontium phosphate. Hands up for silver bromide. That loses. Okay, hands up for copper 1 iodide. And hands up for mercury 2 bromide. Okay, it was the first one. Okay, strontium phosphate. What I want you to do is I want you to take out I want you to take out your data booklet. Okay. There we go. Page 7. No, page 6. Page 6. Okay, what did we say? Strontium phosphate? Okay, let's look for strontium ions and phosphate ions, right? Because it's an ionic compound, we're going to look at the table of solubility for ionic compounds. So, strontium phosphate, where am I going to start on here? I'm going to look at the negative ions. Not always, right? I don't always have to start with the negative ions because there's ammonium in group 1, but yeah, usually. So I see phosphate, so I'm only concerned about this column. And do you see strontium in here anywhere? I do. I see it hidden somewhere in most, right? So would you agree? Would you agree it's only slightly soluble? Okay, let's see. Let's take a look at what's going on. We got strontium phosphate. And sorry, can any amount of strontium phosphate dissolve? Yes. It says it's slightly soluble. That means a tiny little bit of it will dissolve. At the microscopic level, if I add some strontium phosphate, does it dissolve? Yeah. Does it all dissolve? No. So what we're seeing here is we're seeing there's a small crystal of strontium phosphate at the bottom. But did some of it dissolve into our solution? Yes. Would you describe this compound as having low or high solubility? Low. It is, beyond the shadow of a doubt, it is definitely soluble a little bit. But is most, if I added a ton of this stuff, is most of it going to be dissolved, or is most of it going to stay undissolved? Most of it is going to stay undissolved. So is most of it splitting up? Is most of it splitting up, or is most of it sticking together? Most of it's sticking together. And that's what we mean by the difference between a dissociation equation and the major entities. When we're saying strontium phosphate, if it could split up, what would it split up into? So we say we've got strontium phosphate when I add, I'm just going to reset this. When I add my strontium phosphate into water, right? It's a solid before I add it. And I shake up a little bit of it, and when I add it to water, if it could split up, what would it split up into? What's it going to split up into? Wim, thanks for putting up your hand. What's it going to split up into?
3 strontium ions, aqueous, and 2 phosphate ions.
3 strontium ions and 2 phosphate ions. Good. Do you agree? When I add it to water, yeah, it did a little bit of a split up. So we can still write a dissociation equation for this thing. But what happens as I add a little bit more of it? Is it all always going to dissolve? No, there's this tiny, itty-bitty little crystal here. And what do you notice what's happening to that crystal? I don't know if you notice what happened to it. It kind of disappeared, but then the crystals are like forming in other places. Is that crystal staying the same all the time?
Why?
It's dissolving the
So let's take a look at this crystal. And I don't know if there's like a magnifying glass for Windows. This is embarrassing because I should have looked it up. Magnifier. Yeah. Whoa. That is not what I wanted. How do you do this? Yeah, but how do you
Move it to where you want it to magnify.
yeah, lens. Can you kind of see? The program's moving really slowly now because of this, but can you kind of see how parts of this crystal are like leaving and parts of the crystal are reforming all at the same time?
Yes.
Is the size of the crystal, I'm just going to move my mouse away for a second. Is the crystal itself, is it staying relatively the same size the whole time? And so this is something that's really interesting about solutions and precipitates, is that some of these ions are leaving, and as one ion leaves the crystal, what happens? One ion starts to crystallize onto the crystal. You've got 2 processes that are exactly the opposite of each other happening at the same time. It's like we've got 34 people in this classroom right now, Ish, okay? We've got 34 people in this classroom, and so could we maintain 34 people in this classroom all the time when the bell goes? Is that something that's possible? Because all of you have to leave, right? So how would it be possible for us to maintain 34 people in the classroom? You could lock the door. You could lock the door, and then you wouldn't be able to leave. You could still leave because it can't lock from the inside or whatever. But you would be trapped. That's not the same situation as what's going on here, Idris, is it? In order for us to maintain that same equilibrium, for every one of you that leaves, what has to happen?
Someone else.
One other person has to come in. So could we still maintain 34 people in this classroom? Yeah, absolutely we could. As long as we have, when one person leaves, one other person comes in. That's the definition of something we call a dynamic equilibrium. Would you agree there's 34 people in this classroom, and there has been for like a half an hour now, and so we are at equilibrium right now? Would you agree? The number of people in this room is not changing. Is it a dynamic equilibrium? Is it an equilibrium that's allowed to change form? Does that make sense? So there's a difference between a static equilibrium. Static means always the same and never changing. Dynamic means changing, so changing equilibrium. is our population changing right now? Are the same people always in this classroom right now as there has been for the last half hour? Yeah, that's a static equilibrium. We're not changing at all. Nobody's leaving, nobody's entering. We have the same number of people. But that's different from a dynamic equilibrium. Dynamic equilibrium is that the people are changing, but the thing that you're defining, either the temperature or the solubility or the size of the crystal, it's constantly changing because when one thing leaves, one thing enters. Yeah. Wim.
This is kind of like that golden rain thing we were looking at the other day.
It's kind of like the golden rain. That's exactly right. And so when you look at this, I'm going to, I don't know, can that work? No. Blam, there we go. Okay. It's kind of like the golden rain, where if I was to heat up this solution, let's heat up this water. I don't think I can on here, but if I was to heat up the water, what would happen to the size of this crystal? It would get smaller. Why would it get smaller?
Because there's more energy.
Stephanie?
There's more energy.
There's more energy. What has more energy?
The part.
The particles of everything, I guess. But the crystal particles have more energy. And if they have more energy, are they more likely to leave or are they less likely to leave?
More likely.
More likely to leave. So when I heat up this solution, these ions gain more energy. When they gain more energy, they move faster. And so the moving process wins out of the entering process, if that makes sense. So the dissolving process, now all of a sudden, it's moving faster than the crystallizing process. What would happen if I were to cool this solution down? What would happen to the size of the crystal?
Get bigger.
It would get bigger because the particles, do they have more or less energy now? They have less energy, and when they have less energy, their attractions together can make a new part of a crystal. Does that make sense? So that's what we call a dynamic or a static equilibrium. And so this is the last curricular outcome for us to be able to understand. Most substances dissolve up to a certain point, but after that point, a solid forms on the bottom of the container, right? What do we call that, a solid forming in a solution? A precipitate. And we saw that golden rain precipitate form yesterday in that video. The solid, believe it or not, is that solid crystal still dissolving? Are there parts of it that are still dissolving?
Yes.
Yes. But the crystal doesn't change overall because while one part is dissolving, what's happening to another part? It's crystallizing, right? It's forming a new precipitate. So the solid is still dissolving, but it's also crystallizing at the same time. This is what we call a dynamic equilibrium. So here we can show this equilibrium in our chemical equations. And this is something that becomes a huge unit. This becomes, this idea right here forms the basis of 30% of Chemistry 30. So if you're interested in taking Chemistry 30, all of a sudden this idea of, okay, one of these arrows, which arrow, top or bottom, which arrow represents this thing splitting up? The top arrow. And which arrow represents these two things coming together to form a precipitate? The bottom. I'm representing that there's actually two reactions happening at the exact same time, right? There's the forwards reaction and the reverse reaction. And there's a whole class of reactions that we call equilibrium reactions that you'll learn about in Chemistry 30. But for right now, this is all we really need to know. So we will describe this a little bit more. So we have two opposite reactions. Do you have a little, I think you have a little bit of room at the bottom here, right? Yeah, kind of, sort of, a little
Not
bit.
really, right?
Yeah. So you maybe, I don't know, maybe you have room at the top of this slide, or maybe you have room. Is this the very last page?
Yeah.
Very last page, very last slide. Woo. Okay. Two opposite reactions. So there's the one reaction where calcium sulfate is, what do we call this process of an ionic compound splitting up in water? Dissociating. Into calcium and sulfate ions. See, can we still write a dissociation equation even for something with low solubility? Yeah, because you just saw some of it still does break up. And then there's an opposite reaction. What's the opposite reaction of this? The forming, right? The calcium 2 plus and the sulfate coming together to form calcium sulfate. Whoop, no charge. And this will happen for every solid. Every single solid will eventually form some sort of a precipitate. There is always a maximum solubility for any sort of solid compound at all. Take a deep breath. Does it feel good? We're done. What do you want to work on? You work on your major assignment? You're going to work on your review booklet? The key to the review booklet is already on Google Classroom. It's been on there since I made our Google Classroom page. Does anybody need the link to the Google Classroom?
Yes.
There's a Google Classroom. I'm sorry, Stephanie. I made this when you weren't here because I asked us about this. And people were mad at me that I hadn't made it.
I didn't see it.
Totally, yeah.
Can I copy and
Yeah.
that's a yes I can?
A0